You want it? Water. Water. Okay, okay, good afternoon to all of you. I am Professor Nagaraju, Computer Science and Engineering, Department, Yoga University. I was the first batch student of JNTU Anantapur. Today I am going to discuss about intermediate code generation. So today's session contents are Introduction to Intermediate Code Generation, Intermediate Code Generation Techniques, and gate problems and solutions of 16 problems. So these are the today's contents. What is the intermediate code generation? What do you mean by intermediate code generation? It is the fourth phase of compiler design. Many compilers convert high-level language programs to intermediate form and then convert to mission-level language. The main objective of the compiler is many compilers convert the high-level language programs to intermediate form of the language and then convert to mission language. So here is intermediate code generation. So it is intermediate between front end and back end. So a source program, front end, intermediate language, back end, and target language. So here is the intermediate representation. Intermediate representation is a mission independent and language independent of original source code. Generally, the intermediate code is a mission independent as well as language independent. So, for example, so that is the back end. So that is the back end of the compiler. So it depends on the mission. Back end of the compiler, it depends on the mission, and front end of the compiler. So that is, it depends on the programming language. So, but here is the intermediate code does not depend on mission or does not depend on any programming language. So that means it clearly separates the front end from the back end. So that is what are the advantages of using that intermediate code generation. So first one is the clear separation between the front end and the back end. So that means intermediate code clearly separate the front end from its back end. So what is the need of, what are the advantages of separating these two? So that is not important. So it adds possibilities for retargeting and cross compilation. It adds possibilities for retargeting and cross compilation. So cross compilation means once you compile the program on particular mission, so the code may be run on anywhere at any time. So for example, you see that in the Java programming language. So that means we are generating the bytecode. So that is the bytecode. So bytecode can be done on any other missions. That is the bytecode is the intermediate form of the compiler, right? In the same way, so suppose that will be run only on the Java virtual machine. So that is the bytecode, suppose, which is generated in the Python. So that is also executed only Python virtual missions. So that's why here it is very easy to generate a cross compilers. That means that facility is provided by using intermediate code generation. Intermediate representation support advanced compiler optimizations. So intermediate representation supports advanced compiler optimization. So that means at the beginning of the compiler design lecture, I had solved some more C programs. But here is, if you want to solve that C programs, so compulsory the advanced features must be included in the programming languages. So that's why that concept is very easy to add new concept to the intermediate code generation with the help of intermediate code generation. So if the compiler needs to generate a code for several different mission architectures, only one mission architecture is sufficient. Suppose if you want to develop a same compiler for more than one, if you want to generate code for more than one mission architectures, but you write only on one mission architecture, so you can run on any other computer's architecture. That means it is the architecture neutrals. So that is provided by intermediate code generation phase. So if the several high-level languages need to be compiled and any one intermediate code generator is common for all. So suppose you can generate, suppose nowadays we can see that thousands of programming languages are coming. So new programming languages. Suppose you see that Python, so Python are programming like that. So there are thousands of packages are available. But in that cases, for each and everything, so suppose you need not to write separate intermediate code generation. So if you concentrate only front end, the back end will be taken by the intermediate code generator. So properties of intermediate code. Properties of intermediate code. An intermediate language should ideally have the following properties. An intermediate language should ideally have the following properties. So first one is it should be easy to translate from high level languages to the intermediate language, because so that is the intermediate form is also somewhat so the related to high level programming language. That's why it is very easy to write so program for conversion of high level languages to intermediate languages. It should be easy to translate from the intermediate language to, so that is the mission code. So that means here so that is intermediate code is a ready-made code for so converting into mission language. So that's why it is very easy to. The intermediate format should be suitable for optimizations. So that is in the compiler construction where the optimization can be takes place. So only at the intermediate code generation. While you are generating the intermediate code, there only we can concentrate on code optimization techniques. So generally we can say that some compilers are so very more. Suppose you take the C programming compiler, it is a more powerful compiler. So because of so the optimality is provided at the level of intermediate code. So Ratan will explain everything about that, right? So it is very easy for manipulation. It is so that is the next advantage. It is very easy to manipulation. Increase the level of abstraction. It increases the level of abstraction. Intermediate representation. Suppose the same thing, intermediate language may be in different representations. Intermediate language may be in different representation. For example, so the designer of the compiler decide to which intermediate language should be used. That means there are many techniques to implement the intermediate representation. But that depends, the selection of particular intermediate code is depends on the compiler designers. For example, suppose here is you see that there are many intermediate representations in use. One is the postfix notation, so syntax trees, direct acyclic graphs, that is the quadruples. That is the intermediate representation of any programming languages. There are so many intermediate representations are there, but maximum we are using either postfix notation, syntax trees, direct acyclic graphs, and 3 underscore. So for example, you have seen that. So that is in the previous class, I explained that a semantic analysis, that is the syntax tree and postfix expression. Suppose in the second year, in the data structures, in the previous class already I explained that how to convert the parse trees into syntax trees and syntax tree to annotation tree and how to evaluate the things. Another one is the directed acyclic graph. So that means already you have studied in the data structures, 2 types of the graphs. So one is the depth first search and another one is the breadth first search algorithms. That is the third one is, so that is the fourth one is 3 underscore 100. So these are the things. So in the previous class already we have studied postfix notation. So that's why I don't want to go explain how in depth about that postfix notation. On the depending upon the operator, we can call it as a postfix or infix or prefix. Suppose if the operator is in between 2 operands, we can call it as a infix notation. If the operand is that is preceded by 2 operators, 2 operands, so then it is called a prefix notation. So if the operand is at the end, so suppose followed by suppose the operand 2 operands, after that when it comes the operator, so then we can call it as a postfix expression. So in the previous class already I explained that So what are the main advantages of converting the infix expression into postfix expression? So here is the evaluation should be very easy because so that is the postfix expression does not follows any, so that is the parenthesis. For example, in the expression when you are given that more number of parentheses, so that is we have to decide which statement will execute first. That is which operation will execute first. Suppose if you remove these braces, so then it will be, so it will not, it will be executed last. Or suppose when you are keeping the braces, it will be executed first. That means here is the priority of operator and associativity of the operator. That is the, so from left to right or right to right. So that's why here is, suppose when you are using the postfix notation as an intermediate form, so that is you need not to concentrate on parenthesis and you need not to concentrate on the priority of that. So for example, so in the previous class already I explained it very clearly. So that's why I don't want to go in depth, because so after converting that into postfix, so we are getting, this is the postfix expression. So that is, this is the procedure. Here is we are using the stack by pushing two operators and operands and operator. So then here is, so that is output. So that is we are constructing the syntax tree, right? So the next one is syntax tree. So that is another, so that is our construct syntax tree. So already in the previous class, already I explained the syntax trees also. So syntax tree, the parse tree are additional information of with the attributes. So the syntax tree is nothing but is a parse tree plus with additional information. So additional information means either that is the attributes and rules will be added to the parse tree. When you are adding the attributes are, so that is the attributes are attributes and rules. When you are assigning that, it will become a syntax tree, right? In the previous class, this is also one kind of intermediate form of the, so the intermediate form of the compiler, right? So that is the syntax trees also already studied in the so previous class. So already I explained this. So that is the parse tree for the syntax tree. So just we can use like this. But the same thing already I explained that. So next one is the direct acyclic graph. So this is also another method. In a syntax tree, there is only one path from the root. For example, so that is yesterday I explained as a dependency graph. That means that will show how the direction of execution of the expression. But here is another one is when you are using the syntax tree. So there are some drawbacks in the syntax tree. What are the drawbacks of the syntax tree? The syntax tree, there is only one path from root to each leaf. But when you are doing that in a syntax tree, there is only one path from root to each leaf node. So that is when you are using only one path from root to each node means, so that means the length of the tree may be increased, right? So when the length of the tree is increasing, the execution speed will be reduced and memory will be wasted. So the second one is there some subtrees are duplicate in the tree. Suppose when you are constructing the tree, so there may be some duplication within the tree. Suppose if you have taken that a plus b, suppose you have written this a plus b 100 times, so 10 times within the same program. But here is for a plus b, it is a subpart of the tree. So that is 10 times you have to write. Suppose 10 times it is repeated, you have to write the same tree nodes, you have different nodes for 10 times. That is the duplication. But here is suppose whenever you are using that in the direct cycle. So an interior node represents an operator and its children represent the operands. So that means these are the main drawbacks of syntax tree. So these are only one path from the root to each leaf of the tree. So there some subtrees are duplicated in the, there are some get in the tree. And interior, so that is interior nodes represent an operators and its children represents an operands. The data structure. So suppose what are the advantages of using the direct acyclic graph over the trees? The data structure with more than one path from start symbol to terminal symbol. That means here is whenever you are using that in the tree, only one path from root to all the children. But here is, so from the root, so there may be any number of, so the paths may be achieved. So that means here is the data structure with more than one path from start symbol to terminal symbol. So that is called direct acyclic graph. That means any number of nodes or paths may be achieved. But suppose from root to children, so if there are more number of roots, so then we can choose the shortest path. So that automatically it increase the execution speed, right? So such a structure is called direct acyclic graph. That is also called DAG. Most of the people, so they are calling it as a DAG. That is the direct acyclic graph. A DAG gives the same information as syntax tree, but in a more compact way. But here is the direct acyclic graph gives the same information like syntax tree, but it is a more compact way or more abstract way. So more contract and more abstract way. But the parts tree represent each and every details. But when you comes to syntax tree, it hides some details. But when it comes to DAG, it hides almost all the characteristics. So that's why it is a compact way of this one. So for all the 10 sub-expressions, so it will have the root from main expression to sub-expressions. That means it will eliminate all the sub-expressions. So here is also an interior node represents an operator and its children represents an operands. Its children represent an operands. So DAG optimizing the code. So generally the DAGs are used for optimizing the code. So suppose if you want to reduce the size of the code, if you want to write efficient code, we can use the DAG than tree. So that is syntax tree. It eliminates the sub-expressions and duplicate code. It eliminates the sub-expressions and duplicate code. For example, you see that, so in the previous case already was in syntax tree, but here is in the syntax tree, so the same thing. So in the tree, so that is here is a subtree and here is a subtree. But both are same, but even though we are representing this separately. But when you are using the DAG, it removes, for example, so you see that. So this is eliminated, that is the duplications are there. This duplication is eliminated and link will be given as the assignment to this one, because this is the direction, right? This direction will be given to this. So then when you see that equal to, and this subpart is eliminated. This subpart is eliminated. Right? I understood that. What is the difference between a syntax tree and direct acyclic graph? Two are there, but one is eliminated in the directed graph. Or suppose here is also you see in this syntax tree. So suppose in the syntax tree A is equal to B star minus C plus B star minus C. So here is the, when you draw in the syntax tree, so that is here is in the A assigned, so that is the A minus C or star. Here is the same code is it, but here is when you are using same thing, by using direct acyclic graph we can eliminate this and we can make it, we can simplify the code. So that is the main advantages of using directed acyclic graph. That means only for eliminating a sub expressions, so that we can reduce the code size. So automatically it increases the execution speed of the program. So this is the direct acyclic graph, right? So that is the variance of syntax trees. But here is the in the intermediate, in the previous class already we have studied. So that is the parse trees, syntax trees, and the dependency graphs. But why again we are studying that the syntax trees and syntax trees and DAGs means direct acyclic graph means. But when you are making it, these are the intermediate codes. How to represent these codes within the memory? That is a very important here itself. That means our main is we have to reduce the storage capacity means, so utilization of the memory is very efficiently, or next that increase the execution. But here is when you are representing the code is intermediate form, how the syntax trees or DAGs are stored in the memory. That is the main concept in this intermediate code. There, so I use that how to give the meaning and the evolution order, right? For example, you see that in some, so that is invariance, it is sometimes beneficial to create DAG instead of tree for expressions. This way we can easily show the common sub-expressions and then use the knowledge during code generation. For example, when you see that A plus A into B minus C plus B minus C into D. So for this code, so suppose when you are using the DAG, you see that, so first one is suppose B minus C, it will executing B minus C, and the next that will be comes to into star A. So suppose this expression, because the evaluation should be from left to right, because here is all that is arithmetic operation. Suppose this minus, so that is also, so suppose next one is into A, and that is added to plus there. So suppose here is again we are in D, and next suppose plus A means directly we are adding link to this one without using separate A, then we are in. So that, so suppose if there are 10 duplications are there, so then automatically memory will be wasted. So how we are representing this expression in the computer, how we are storing in the memory. So generally you see that this is the expression, previously this one, and this expression is there. This is the part, so this is called context free grammar. This is called context free grammar, and with the help of this context free grammar we can draw the any trees, sparse trees, either top down approach or bottom up approach we can use, and we can draw the production. So this context free grammar is converted into, so that is by adding converted into context sensitive grammar. Context sensitive grammar by giving semantic rules and attributes. By adding attribute and semantic rules, we can make it as a context sensitive grammar. So that is in the previous class already I explained that how we are converting. So here is we are adding information e dot node. So new node. Here is we are creating new node. So in the data structures you have created the node with so that is the value, left subtree and right subtree. Here is also we can use for this one. So the plus is the value, e1 dot node and t dot node. That means here is it is a node, this is the node and this is the plus. That is the plus. So terminal operator and two nodes are creating. Here is e dot node is equal to new node minus e dot node and dot node, and here is where dot node are we are converting like this. Totally t dot node is equal to new leaf id entry. Here is in the leaf node id, that means identity value or number. Id entry means this entry shows the table, so that is the symbol table entries. Suppose this will show the symbol table entries. And t node leaf number and number dot value, number and number dot value. It is a constant value and that value is assigned to this. For example, so when you are taking that, how to represent each and every node. For example, here is a P1. So that is a P1 is a leaf node. ID, comma, entry A. So suppose in the previous case, you see that first suppose you have taken A. So that is the A means you are taking P1, leaf ID, comma, A entry. That means entry pointer of symbol table. P2 leaf ID entry minus RP1, so that is the same. P3, P4, P5, P6 up to P13. So that means here is some pointers we are using and we are storing these pointers in the symbol tables. Suppose if you want to evaluate this, so then directly you can use the syntax tree or DAGs. But so how we are representing this in the memory means, for example, so each node can be contains three parts, right? That is the pointer, left subtree pointer, right subtree pointer and value. So these values can be represented in the symbol table like this. Value number method used for constructing the DAG. Value number method means, for example, when you are taking this DAG, suppose here is the entry of this symbol table. We can use it as a symbol table. So you see that the plus, and here is the plus is there, but here is when you are using that, it contains the left pointer and right pointer. Left pointer and right pointer. So that is when you are using that is the left pointer and right pointer, we can say that it is a left pointer and this is the right pointer, and here is the same thing. Here is we are copying the values in the symbol table. The first one is the place, and next that is I, we are taking that. So I is stored in the second place, that is in this case. So that is the left I, this is the left node, and that is the right node will be represented in the position of this. So that means here is, but when you are using this, so then, so suppose here is, whenever are using that, we can use the values of this one. So suppose here is the symbol table, so we can store the values, 2 pointers and 1. So that is the thing. So suppose here is a non-terminal and 2 pointers. So but when we are using that, already we know that. What are the main drawbacks of trees in binary search tree? For example, there are so many binary search trees are there. So binary search tree, ABL tree, B trees, ABL trees, red black trees, splay trees. So that is the ABL trees are like that. So the ABL trees and B trees and B plus trees and hash functions are there. But here is when you are using this table, suppose if the tree is the only left, so suppose here is left skew tree or right skew tree, there is a chances of wasting lot of memory. There is a large chances of wasting. So the loss of the there is a chance of losing the memory of this. Do you know how to store the values in this case? So suppose here is when you are using this. So but so here is we can take the tree, and here is we are taking the tree, and this tree is stored in the symbol table with 3 fields. One is the value field, left subtree pointer and right subtree pointer. But here is the number is there. In this case, you see that number. But when you are using the number, so that is the number directly we can store the value in the symbol table, because for constants that will be stored, and it will be the number value that will be specifying of this one. This is the node. Number is equal to node value, and based on that it will be evaluating. So that means, so that is the value number method for construction of DAG. Have understood that? So suppose first one is, if you want to use, that is the syntax tree as the intermediate code representation. So the first one is you have to take the parse tree, context free grammar. With the help of that context free grammar, so you draw the parse tree as a top down approach or using bottom up approach. So after that you convert that so that is context free grammar to context sensitive grammar by adding attributes as well as rules. So then you construct the, so that is the syntax tree. So after that, by giving the values to the syntax tree, so then you convert that into, so that is annotated tree. So from that annotated tree, you construct the dependency graph, and with the help of the dependency graphs, you convert that into the DAG, direct acyclic graph, and that will be stored data in the value. Suppose this is the, so here is the main drawback is we are using the value number method, so there is a memory may be wasted. So that's why you can go for some other techniques for this. So that is the form of tree address instructions. Most of the cases, most of the 90% of the compilers, so they are using form of tree address instructions. Tree address instruction. So in this class, I will explain. So that is each and every instruction. That means how the arithmetic operators are executing, how relational operators can be used, and how the go-to statement will work, and how the procedure will calling, how the pointers will be executed or converted into the tree address code like this. But in the beginning class, I explained that short circuit rule. The evolution order. So for this one, I will explain how they are written code in the, so there is tree address instructions. So first one is, you see that we can write the expressions like this. X is equal to y operand b. That means all arithmetic operators. So x is equal to y plus z. So this is the tree address code instruction. Something we can all arithmetic. X is equal to y plus z. X is equal to y minus z, like this. Or second case, we can use x is equal to operator my. Suppose here is, so that is the unary operators are there. Unary plus or unary minus. Here is we can use. So suppose here is when you are using that, here is we can write like this L. So go to L means go to 10 or something state label we are giving. So next we are using the if else statement. Next one is if else statement. So then if else statement, if X is true, go to L and if false, X is go to L. So suppose here is we can use the any operator. Suppose a go to statement or relational operators we can use within the if statement and procedure calls. For suppose sometimes we are calling parameters. Suppose a of x comma y, we are using a of x comma y, or suppose function we are writing sum of x comma y. That means here is you can execute this sum, square root of x. So like this, but how the arguments will be passing, how the compiler will identify these arguments. And here is you see that array we are using x is equal to y of I or x of I is equal to y. But in the new languages we are using both the conditions, x is equal to yi and x of I is equal to y. So that is the array operations. But how the arrays are stored in the memory? And x is equal to address, that is the pointer operator, and x is equal to this pointers. So that is generally we can observe these kind of statements in any programming language. Suppose if you want to perform any arithmetic operations or anything, we can use x is equal to y plus z or something like this. So that is x is equal to minus 1, x is equal to y, and go to statements, if else statement, while loop, do while, for loop are structures and pointers. How to represent with the semantic code, how to represent the semantic code, and how to evaluate that semantic code by using three addressing instructions, and how that will be stored. So that is some of the problems I will explain, and how we are using and how we are evaluating the things like this. Type checking, arithmetic operations, relational operators, go to statement, how to represent the functions, and everything will be written in the form of tree addressing code. So now we will explain some of the tree addressing codes like this. The grammar for the intermediate language is shown in the previous slide. So that means this is the grammar. So for tree address intermediate code, the grammar means, but these statements, this syntax, you have to store in the data. In the what forms are there to store the data to reduce the time complexity and space complexities are important. The grammar for the intermediate language is shown in the previous slide. A program is a sequence of instructions. The instructions may be label. That means here is this has no effect, but several serves only to mark the position in the program as a target for the jumping. So label means go to L. L means L is the label that will go to the particular statement and it will move the thing. Or assignment operators we can use, an assignment of an atomic expressions. That means here is we can assign the values. So that is the x is equal to x plus y or something like this. Unary operators we can use, that is the unary operator, x is equal to minus y or x is equal to plus y, like that. And binary operators we can use, a is equal to b plus c. So that means the binary operators we are using. And the transfer from memory to the variable, that means arrays, how to represent the arrays like this. Memory locations in the atomic, adjunct labels, that is the go-to statement, how to represent go-to statement in the intermediate languages. A function call, that means here is suppose when you are using the function call and function, how they are representing in the intermediate code. Or next, that is the thing like this. That means this is the grammar. But in any programming language, we can see that operations like this. All the operations in this class, I will explain how to declare the variable and how to, so that is use the arithmetic operations, relational operators, control statements and things. So I will explain that how that will be stored in the intermediate form. So because almost all the programming languages using this formats, right, this grammar. So that's why, for example, you see that example in 3 address code, but how the expression will be evaluated. You see that. So here is we are using the DAG. So that is the direct acyclic graph. And here is you see that first we can write b plus b minus c. Here is we are writing b minus c. After that, so that is the b minus c into a. After that, so that is the next one is the a is there for this one. That A is again directly connected to this, and here is for this one, so that is the plus, and here is a B minus C, so that is the B minus, so that is sorry, B minus C, that is the same operation. So from this star, that will be using this by eliminating duplication. So next this B minus C into D, this is the expression that we will be taking after that. So both will be multiplied and then we are getting the plus operation. Actually this is the procedure, but how this can be represented in the form of 3 address code. So this is very important. You see that. So first thing is we are using T1. These are the temporary variables. Temporarily we can use in the memory. So T1 is equal to B minus C. This will be taken into a temporary variable. T2 is equal to A into T1. T2 is equal to this is the T1 into A2. So why you have to intermediate code means, suppose if you are using again and again, it takes the more time. Suppose here is A into this, and next here is 3 is equal to A plus T2. T4 is equal to T1 star D. So that is the T1 means already we have taken B minus C. So the T5 is equal to T3 plus T4. So here is the 3 address code means here is we can use 3 operands and 1 or 2 operators. That means here is the maximum, at most we can use 3 operands. At most we are using 3 operands. That's why we are calling it as a 3 address code. But you see that here is T1 B minus C. That means the 3 operator, only 3 operands are there, and one assignment operator and one. So that is any relational, any arithmetic operations like this. But how this will be stored in the memory? So these DAGs can be stored in 3 ways. That is data structure for 3 address codes. That means, so how this DAG can be stored in the memory means we can use the 3 addressing code. So that is the data structure for 3 addressing codes are, one is quadruple, one is quadruples. That is the one data structure. And that is here we can use the 4 fields. Quadruples means we can use 4 fields. One is the operator. So first one is argument 1, argument 2, and the results. You see that. So that is, this is the result field. T1 is the result field, and that is the assignment operator. So that is the operator is the minus. So B and C are the arguments. So that means here is in the quadruple, it consists of 4 fields. It consists of 4 fields. Opcode, so that is the operator, argument 1, argument 2, and the result field. Right? So these 4 fields you have to store in the database. Later on I will show that. So next triples. Triples means so that is the temporaries are not used and instead references to instructions are made. Here is the results and operator and operands are directly we are storing. So instead of storing that, we can use the pointers. That means pointers. Already we know that how efficiently we are implementing that code with the pointers. Suppose in the real life dictionary, if you want to implement the real life dictionary, how many minimum number of pointers is required? Minimum number of pointers. But most of the people will say that 26 because there are 26 alphabets. But here is, so the entire dictionary, even that maybe contains 10,000 words, we can implement it by using with only 2 pointers, 2 values, 2 variables. One is the value and another one is the pointer. Variable and a pointer. With the help of these 2 pointer and variable, we can represent entire dictionary. So that is called triples, right? So next, indirect triples. Indirect triples means, so for example, separately, but here is we are using the location of the variables. Later on I will show that. Location of variable, and here is indirect triples means it is separate list will be used for referring the addresses. For example, in the textbook you see that index and chapters. But in the index, so that is the index will pointer, it will represent the separate pointers, right? For implementation of 3 address codes, we can use 3 data structure. First one is, see that, suppose the expression is B star minus C, B star minus C plus B star minus C. We are taking that is B star minus C and B star minus C. So this is nothing but B into minus C minus C. So next to plus B into minus C. Because so many cases we can see like this, right? So but when you are taking this expression B minus C, but in the quadruple, how to store the values? So the first one is, you see that the first, so that is already this is a 3 address code for this expression. T1 is equal to minus C, we can assign, and T2 is equal to B star T1. Just you see that minus C, why you have taken the first minus C is evaluating means, so B is already in the memory, but C is in the register. C is the second argument is in the register. That's why directly we can assign values. So that is the minus 3, and T2 is equal to B star T1, T3 is equal to minus C, T4 is equal to B star 3, T5 is equal to T2 plus T4, A is equal to T5. So in the quadruple, how the this 3 address code will be converted. So then here is the first one is the minus, operator is minus, argument is only C, and the resulting field is T1. There is no second argument, right? Or in the second case, so that is the star. Star is the operator, and B is the operand, and T1 is the operand, and T2. So directly as it is, we can store. That is a quadruple means it is a one kind of symbol table. That's enough. But how we are storing the values in the symbol table? What data structures we are using? That represents with a quadruple. Suppose minus C and no operator 3. So that is for this one. Star B T3 T4. So this is the quadruple. So that means here is how many fields we are using? 4 fields. That's why we are calling it as a quadruple. So we can consider as a quadruple. It is very easy to implement, but here is the memory will be wasted and some execution speed will be reducing, searching time. So that's why this is the, I have understood that. What is the quadruple? So that is the operator, argument 1, argument 2, and results will be stored. But the same operations in the triples, that means only 3 arguments we are using. But here is you take the positions 0, 1, 2, 3, 4 or something like this. Here is we are giving indexed positions. But same thing, minus C we are using this one. There is no second operator. In the second case, you see that star is there, star B star T1. So the star B, and next one is here is we are taking T2. But instead of taking T2 and this one, so we take the T1. From where we are collecting the T1? So that is the T1 is writing that position. You see that? So that is the position we are writing. So 0. So that 0 is written in the brackets. This will be represented with the pointer. Right? You should understand that why you are using the pointers. But how the pointers are stored in the symbol table. Now suppose if you are not using the pointers, so that is the data will be stored like this. So when you are using the pointers, the data will be stored like this. So here is, you see that in that case, suppose here is, but here is 0 is stored. So next to minus C, and third case star B plus 2. B plus 2 means that is equal to whatever you have done this one. So T3, so that will be taking. That means here is we are not using third variable and only we are taking the second position value B and minus C. This value will be taking. You see that? So that is we can eliminate a third variable. That is the result variable can be removed from the triples. But here is only we can use 3. So that's why in the most of the GATE examinations are so in any external or internal examinations. So in the C programming they will ask the question. So they write a program to swap 2 numbers without using third variable. Without using third variable. So that they are asking, why they are asking without using third variable means, but that specify the these triples. But when you are using that, it will be specify the same variables. Our next but is in indirect triples. How we are storing means same this triple and separately these pointers are stored in separate table. The pointers are stored in separate table in one dimensional. So that is the list of element. But here is, so instead of giving this index number, the pointers will be stored in separate memory location. Suppose that's why here is, it is very easy for searching time. Suppose B star means immediately that it comes to the 35 position and it will take the value of this. This is the indirect triples for storing the syntax trees or directories into the converted into 3 address code. I have understood that this 3 address code is, so the stored in the symbol table in the form of a quadruple data structure or triples data structure or indirect triples. So depending upon the usage, either if you are using the pointers in your program, so then you can use the triples. If you are using that is a shorthand arithmetic expressions like that, we can use like this something, and here is the quadruple that will be taking the values of this one. So these three are the examples how the 3 address code can be stored. I think you understood that, right? So suppose these are the 3 address symbol table code. Because when the people will see the slides, right? So that means these are the things we can use in the wireless. Answer that 3 address code means, suppose here is the 3 address code. So when you are using 3 address code means here is the maximum it uses is the, so that is the 3 operators. That means one is the result operator, argument 1 and argument 2 and 1 operator. That's why we are making it, converting it as a 3 address code. But how the 3 address code will be converted and how that will be stored in the symbol table. So 3 address code can be stored in the symbol table by using the quadruple method or triple method or indirect triples methods, right? So this is the things. But here is now you see that, but our intention is how to declare the variables. For example, in the C programming, we are writing int a comma b comma c or float x y z. Either in any programming languages, we are declaring the variables, except in the Java and so suppose in the R or the Python. So suppose in the C programming, when you are declaring the variables, but we don't know how the values are assigned. So that means that whenever you see the declaration part can be shown so in the compilers, right? For example, so that is the general structure of declaration is like this. Suppose here is you take that D is a non-terminal symbol. It shows a sequence of declarations, a sequence of declaration. For example, when you see that the C is, so suppose B, you see that B is a non-terminal, it represents the data types of int or float. It represents the data types of int or float, right? So, but here is when you are using, so D is equal to TID or D or epsilon. So that is the grammar can be represented like this. But here is the B, T means T can be used, there is series of declarations and T represent, so that is the integer declaration of variables. But here is you see that a C is a set of, so that is either it may be record, it may be array, and B means it is either integer or float. But when you are identifying that integer or T, the B can be replaced with the integer and the C can be replaced with the number of values or no values. Or records also represented the same thing like this. Here is the brackets, within that we can write all the data types. Suppose character, so that is the name, that is the string name, or next integer roll number, integer mass, average and float like this. We can write the records. Records are nothing but structures. But here is the structure syntax is declared in the intermediate code. So like this. Suppose here is a number code and B integer or float, C epsilon are integers we can use. And how these will be stored in the memory locations. But when you are declaring the variables, we can say that, so integer occupies, so that is the 2 bytes of memory. But nowadays, it just you remember that int means, but in the C program we can say that 2 bytes of memory. But in the Java we can use it is a 4 bytes of memory. But whenever in gate problem, whenever we get that type size of the integer, you take the 4 bytes, because the 2 bytes have gone. But in the C compilers we are saying, but IDs we are using in the C compilers. ID integrated development environment. There also we are using 4 bytes. So that's why when it comes to integer, you take the 4 bytes. Instead of 2 bytes, you take the 4 bytes, right? But here is suppose how the memory is stored. Suppose when you are declaring int a comma b comma c, float x comma y, how that will be. So that is allocate the memory in the symbol table. Here is you are declaring that. So the storage allocation, you see that. So T, so that is the T is equal to BC we are writing. T is equal to B and C. Already you say that this is the array or integer. It can be replaced with the integer or float. So then here is you see that T is equal to B dot type. Here is T is equal to B dot type. So B dot type is int or float. We are saying that here is the B dot type is so int or float. Width is equal to B dot width. Width is equal to B dot width. Width means suppose how many bits, right? Suppose B is the integer. Here is when you are taking B is the integer. B type is equal to, we can write integer. B type is equal to integer. B dot width is equal to 4. We can write B dot width is equal to 4 bytes. Suppose B tends to float. B dot type is equal to float or B dot width is equal to 8. So that is 8 means it is a double. Double is also one kind of float. Or C epsilon, C dot type is equal to T. So C dot type is equal to T and C dot type is equal to width. C dot width is equal to this one. Suppose if it is an array, if it is C is array of number dot value, comma C dot type. So that is the number and C dot type. Suppose if it is an integer, it takes the 4 bytes. So C dot width is equal to number dot value into C1 dot width. That means here is if array contains suppose array contains 10 values. So 10 into 4 that is equal to 40 bytes of memory will be occupied in the Java programming language. So then here is the storage can be represented in the intermediate code for each and every variables like this, right? But here is the storage for local variable. Suppose if you are declaring the integer int 2 comma 3. So this is the array. Suppose you say that int 2 3, but here is I did not mention that name. That is the int 2 3 array into 2 3. But this array, suppose when you are using that 2 3. So that is the int, suppose here is we are taking 2 3, that is the 2-dimensional matrix, and here is the name of the array is 2, and here is we can represent whenever we are giving the int array of 2 comma 3, immediately the compiler will convert that into in this format. Array 2 comma array of 3 integers. That means here is this array contains 2 arrays with 3 integer values. 2 arrays with 3 integer values. That means 2 one-dimensional arrays. Each one-dimensional array contains 3 integers, right? So then whenever given the 2-dimensional, directly it converts that. So that is the 2 arrays with 3 integers. So after converting that into like this, and memory is allocated like this with the help of this diagram. First we are assuming that you see that. So int. So that is the data type. We are taking the integer of this one int. Here is in integer. And next that integer will be assigned to that integer. Width is equal to 4n. And that will be assigned to t. So next here is the t to c. C is equal to again we can assign type array to of this one. So next that will comes to this place. After that will be C is equal to type is equal to integer width. Type is equal to C. Say that type is equal to integer width because it is a single one. So that is the type is equal to integer width. And next this to second case. That means here is integer type is 3 means 4. And here is how many values are there? 3 values. So 3 into 4 12. That will be taking 3 into 4 is 12. That will be evaluating. And next here is 3 into 4 12. So 12, how many rows, how many arrays are there? One dimensional 2. So 12 into 2, that is equal to 24. So 24, and finally it will assign the 24 bytes of memory for this array. Have you understood that? How the memory is allocated for the 2-dimensional matrix? So this is the very important. So that's why here is. But suppose if you want to develop a new compiler, so that is you must to be aware about this also. So that is here is you have to see the first we are taking integer and this one t and directly we comes to like this and here is the first one is where c is equal to, so in the declaration type c type is equal to t c dot width is a 4, t is a integer type data type. So then here is that will go to this type dot array. So each array contains 3 elements and there are 2 arrays. So just read like that. So that is 3 into 4, that is 12. And here is a 2 arrays, that is a 2 into 12 is equal to 24 and 24 will be assigned to values. 24 will be assigned to array. That is the 2 arrays, 3 elements, 3 integer values. You have to study like this, read like this. So the 2 arrays with the 3 integer values. But in the general thing, you need not study, read like that. But here is that is the thing that will be converted. Memory will be allocated for arrays. Have you understood that? How the memory is allocating? Right. So that is for declaration. Records can be, you see that records also we can allocate same thing. And already I explained the type checking. So either that is a what type of data variable. Suppose in the expressions we can use like this. We can construct the tree and here is in the expression type 1 is equal to type 2 and type 1 is equal to integer, then it will execute, else it will generate error. In the previous class already I explained this type checking. I don't want to waste the time by checking this one, right? So now you see that the control flow. So that is how the control flow will be executing. Generally we know that Boolean expressions are often used to alter the flow of controls. Generally if else statement, switch statement or for loop, while loop that will be used to alter the flow of controls, compute logical values. So but how this will be working? For example, I will explain that. But in the beginning class, in the beginning class, I had given this program, but I explained that what is the answer. But here is suppose whenever at that time, so that is the 3 students they asked that why Z got only 1. But here is you see that. But in this program, but whenever are using this program, here is we are declaring 3 variables x, y, z. And here is x, y, z are is equal to 1. We are saying that x is equal to y is equal to z. And you see this expression. So here is I am using increment operator, R operator and R, X and operators. But here is when you see that most of the people, they will think that, so print percentage X, percentage Y is equal to percentage D, Z is equal to percentage D, X comma Y comma Z. So but when you say that, most of the people will say that C is correct because will think that, so that is the 2 comma 2 comma 2. We will that 2 comma 2 comma printing. Why? Because we are in x is equal to y is equal to z is equal to 1 we are given. So then here is we will think that here is, but all are incremented. Pre-incremented means the first value is incremented. The first value is incremented and then the value is assigned to z, right? So we are, that is the rule. But here is also what we will think, plus x plus y plus z. 3 pre-increments are there. So but most of the cases there may be chances to think that, so that is a 2 to 2 like this. But exactly here is the answer is only what? A. That option answer is we are getting only A. So this question arises by 3 students. Why we got only this 2? So suppose the option is, but this is wrong. This is wrong. Why? Because, and here is we are using R operator. We are using R operator. So this concept is called as a short circuit rule. Short circuit rule. This rule is imposed in the compiler. So short circuit means, suppose here is we are taking, suppose x, suppose we are taken x is equal to x and y. Suppose if we are taken x and y with R operator, x and y with OR operator, we can say that here is, for example, here is when we are in x is equal to 1, 0 and R is 1. So that is 0. Or here is this is 0 or this is 1, or we can take that is the 1 or 1 1 and this is the 1. 0 0, this will be the 0, right? But in this case, you see that. So suppose here is, so suppose when you say that, suppose if either x is equal to true or y is equal to true, the answer is true. Answer is true. If x is equal to 0 and y is equal to 1, then the answer is true. But here is, suppose when you are using x, y, z is equal to 1, we are taking. X, y, z is equal to 1. That means first you see that in this expression, x plus plus and R operator is there. So if x value is 1, x plus plus means only x will be incremented by 1, 2. So that is x value will become what? 2. So after that, if it is a 2 means it is a non-zero. Non-zero means, so it doesn't depend on the second part of this one. It doesn't calculate the second part, but it is ignored by this compiler. Only it executes plus plus x. Why it is ignoring? 3 operations you have to perform. That is the first y will be incremented 1, z will be incremented 1, ampersand operator, that is a condition, and condition should be checked and R condition should be checked. So that means here is the time wasting process. That's why if that is x is equal to okay, then what? Why you need not to bother about the y? You need not to bother about the y. That's why. So first, whenever see the compiler, x is equal to plus plus, x is equal to, so plus plus when you are using that, so then here is 1. So here is what operators we are using? R and. So that is the compiler ignores the part of this. That is the compiler. So ignores this part. The compiler will ignore this part. Compiler will ignore this part. So that's why here is the, what is the value of x? X is equal to 2. X is equal to 2. You got this is the x is equal to 2 and y does not increment. That's why we can write that is the y is equal to 1. But you may think that the plus plus is assigned to z. That question the students have been asked. So in the question. So suppose here is x, z, why you got only 1, why can't you 2? Means here is we are using, so that is the relational, that is the logical operators. The output of logical operator is what? Either 0 or 1. But here is a 1, so that's why here is plus plus 2 is not equal to 0, it is a true, then 1 is assigned to z. 1 is assigned to z. 1 is assigned to z. So this is called short circuit operators. Right? I have understood that this is the short circuit operator. So this short circuit operator is implemented in the intermediate code for increasing the execution speed of the program. Now we can see that the C compiler is a more powerful compiler than any other compilers. Why? Because so there are this kind of, so built-in operators are available, right? I have understood that clearly. So why you got this one is the answer is -2. So that is the only, so A is the correct answer. X is equal to 2, y is equal to 1 and z is equal to 1. Here is because in x comma y you are taken x is equal to y is equal to z, and here is x plus plus means when it is a true, that does not depend, that will not evaluate the second part of the logical operators. That's why here is this is true means that will be assigned to z. So that's why here is we are using this. Suppose if here is we are mentioning that is -1, so then it will be 2 2 2 or like this. But that knowledge should be required. For example, if we are taken here is, so that is the 0. Suppose if we are taken, for example, in the same program, you see that suppose if we are taken here is the -1. When you are taking the -1, here is the z will be 1 and x will be 1 and y will be 1. Suppose if we are taken that is the minus, so that is the minus means plus plus means 0. So that is x is equal to 0 or y is equal to 0, z is equal to 0, then z is equal to, that will be right. Suppose when you are taking the 0, 1 1 1 it will read right. Suppose -1 it will write 0 0 0 0 0 0. 0, like this, right? I answered that this is the short circuit rule. But in the intermediate code, how they are representing, I will explain. So here is, for example, you see that, so that is in the intermediate code. Suppose in the 3 address code, how they are written the code like this, you see that if x is less than 100 or x is greater than 200 and x is not equal to y, then x is equal to 0. So this is the if expression. But here is also we are following the short circuit, this same code as implemented in the intermediate form, right? So for example, you see that if x is less than 100, if x is less than 100, directly go to L2, x is equal to 0. You need not to bother about that. So once suppose x is less than 0, you need not to consider this condition. Definitely it will be false. So that's why you go to this one. Or if x is greater than 200, if greater, go to L4. So again you have to check this condition. How do you have to check this? Because here is you are using the AND operators. Compulsory both the relational operators should execute. So greater than 2, then go to this one. Else that is directly that will come to this place. If x is not equal to y, go to L2. That is x, that is true, that is x, or else go to 1. Else go to 1. So this is the short circuit code, so written in the intermediate form. So that's why while you are executing this program, if you try for this program, you can get the answer is x is equal to 2, y is equal to 1 and z is equal to 1. Right, I understood that. So if you want to become a good programmer in either C or data structures or in any programmer, so you must concentrate on the compiler design. So because without knowing the rules and regulations, it is not possible, right? But most of the cases they will say that it is short circuit rule, but how the short circuit rule will be implemented in the compiler means like this. Understood this? So next flow of control. Suppose if statement, how the if statement will be implemented with the help of this. For example, in the if statement, you see that if B S1, if B S1, else B2. Or otherwise, while loop you can use while B do the statements. So here is this how the if statement or the flow statements will be implemented in the in the form of intermediate code means. So in the first case, you see that S can have the form of if B greater than 1. Suppose here is the B is a code, it is what relational operator. Either this may be having either true or false. Suppose if I taken A is less than B, or true or false we are getting. So first we can consider we can evaluate the B value. So we can evaluate, just you see that we can evaluate the B value, B dot code, and either B dot code to assign it is a true or false. So depending upon this value, it will take the true or false. If the B dot code is true, then that will enter the S1 dot code. That is the S1 dot code will be executed. If B dot code is false, directly that comes to next stage. So that means this code is not executed. This is the if statement. And for example, you see that in the same way. So suppose if else statement. Suppose here is, so suppose in the second category, you see that here is, so suppose first B is calculated, B dot code is equal to true, then here is label we are writing B dot code colon. So that is S1 dot code will be executing. After executing S1 dot code, go to S dot next. Go to S dot next. That means that enter into the last statement. That is the next statement of if else statement. Or that is the next statement of this one. So suppose here is we are using the statement like this. So that is it is evaluating B, the code is executed, also go to next statement. This else part does not exist. Suppose if to B dot false is equal to true, so then so directly that goes to the B dot false label, and S2 dot code will be executed, and next that will comes to this place. So this logic is included in the compiler design in the code optimization technique. So suppose you see that while loop, how that while loop is executing. So that is here is also condition is true. Suppose while, as long as the condition is true, the statement 1 is executed, else it will be not executed. For example, first it calculates the B code, B dot code begin. So that is the statement will start with the open braces and close with the begin. B dot code is true, and B dot code is S1 is executed. Again go to B. Again go to B means that will comes to this place. But you should remember that in the assembly language are there we can't use for loop, while loop and do whiles. Only if go to statement only we can repeat. But nowadays we are also using something. But in that case begin or this one. Or so suppose if it is a false, that will enter exit the things. So this is that is the semantic code for regeneration code. This will be written. So that is the same thing we are written separately. And here is a b dot is equal to new value. So after calculating the expression, that expression value is assigned to new label. New label means either true or false will be assigned to B. And if B is the false, next statement will be execute or like this. So that is the S is this one. And the while statement is also we can use execute, already explained. Suppose in the boolean already, so that is be patient. So that after that I will explain 16 gate problems on this, right? So just this is a very important lack of this tree addressing code. Most of the people they are failing to write the programs. They are failing to write the programs in correct manner. So that is the production. B tends to B1 or B2. That means here is in the true B1 is equal to true, B2 B dot true. So that is the B1 dot false, new value will be getting. B2 dot true, B2 dot true, B2 dot false, B1 dot false. Suppose if the conditions are true, then that's depend on the code. B dot code. B dot code is equal to B dot B1 dot code or label of B1 dot false or B2 dot code. So suppose here is we can use label. That is the label here is we can use B1 dot code or B2. Or here is also same thing we can implement. So that is the intermediate code part. So that is the Boolean operations. OR operation and that is the logical OR, logical and Boolean operations means whatever the expression getting output, that is the Boolean operation. Okay? But don't think suppose here and OR, these are the logical operators. But there may be logical operators or relational operators, they produce Boolean values. That's why we can represent these values like this. So that is three address code for expressions. We can use suppose a simple expression. Suppose C is equal to A plus B. When you are writing that, the expressions can be, first thing is we can consider the grammar, and next we can construct the parse tree, and we can convert that into syntax tree. Syntax tree to annotate this with using this grammar, we can convert that into syntax tree. By giving the values, we can make it as an annotated tree. After that, we can use it. So that is a dependency graph for showing the direction of execution. After executing, the results will be stored in the intermediate form like this, right? So that is the increment operator translation. So this is the code for increment and decrement, plus I minus for incrementing. We can take the value. Suppose here is, so grammar we have taken ID is equal to E, and E is equal to E plus E2, or E1 is equal to, you can take the minus. Suppose for decrement we can use the minus, or increment we can use the 1 is replaced with the, suppose I is equal to I plus 1. So suppose here is ID, we can replacing this. Suppose this is replacing with the E. So that is the variable and the ID address. Get generate, that is the E dot address is equal to E1 dot address plus E2 dot address. We can take the values. First one is E dot address. We can create new node and we can create the value by using this expression. Right? This is the increment translation of this one. The translation of switch statement. You see the translation. I don't want to go in depth about that. You see the switch statement translation. We have case label and how we are getting that. So that is the E dot type. Suppose in type conversion into the evaluation. How the expression will be evaluating. E dot type is equal to maximum of E1 dot type, E2 dot type. So that is a widening. So that means here is, for example, so do you know what is the importance of this code? Widening we can call it as a narrowing. Widening and narrowing. Widening means the converting from lower data type values to higher data types, and narrowing means for higher data type to lower data types. For example, suppose if we are taken the integer, if you want to convert that into float, externally we have to convert. So suppose if you want to convert that float to integer, So that will be converting into, that is called narrowing. But here is how the data type, one data type is converted into another data type. And here is we are taking the grammar like this: E tends to E1 plus E2. E dot type is equal to maximum of T1 dot E1 dot type and E2. Here is we are creating the, so what is the maximum data type of these two? Suppose if it is a integer and it is a float, it will take the maximum. So that is A1 is equal to widening. That is a widening A1 address type. With the help of this, so that will be widening. That is A1 will be so converted into A2 is equal to widening 2 will be with the same data type we can replace. So that is the E address is equal to new temporary, and the generate E address is equal to A1 plus A2. With the help of this one, for example, sometimes in the Java we can see that, suppose if you are writing the program roots of a quadratic equation, if you are declaring the variable R1, R2 as the float, automatically it will be converted into doubles. Automatically it will be converted into doubles. That is called widening. But how that will be automatically converting? Because of this one. For example, if you are declaring the variable is, so that is the float, we are given float A is equal to 2. Then the 2 is the integer and float A value is, data type is float. Then by using this expression, so the 2 is converted into real value or floating value, and that value is used for expressions, right? So this is the, so that is the definition translation. So the DDT of this one, how to converting widening to narrowing. So this intermediate code is written in the compiler. Based on this only, it will converting narrowing to widening and widening to narrowing like this. So these are the main things of, that is the intermediate code, right? I've understood that. So the intermediate code is a fourth phase of compiler, and it is a intermediate, it is a middle of the front end and the back end. So that's why the intermediate code is so independent of programming language and independent of the mission language, right? What is the main advantage of converting the high level code into intermediate code means, so it clearly separates the front end and the back end, so that it is very easy to, so that is the converting, it is easy to generate the cross compilers. Like the cross compilation means, suppose you are using creating the bytecode, right? This is the one kind of intermediate form of the thing. Bytecode is one kind of intermediate code. So for example, when suppose you see that, why, what is the difference means, for example, you see that as a software engineers, we are all software engineers. That means we know, suppose we can switch on the computer, we can write the program and we can execute it, we can see the results. But we don't know how to, so what are the parts of the computer, so what is, how the microprocessor manufactures, everything is hidden from us. But in hardware engineers, they know everything about that hardware part. They don't know any C programming or something like this. That means here is from hardware engineers, the software part is hidden. From the software engineer, hardware part is hidden. Both are independent. But suppose if you ask like this, if you know, if you assemble, if you manufacture your computer, then only you can use the computer. So no one will use the computer. So in the same way, the front end and back end, we are good at front end, we can develop the front end, and somebody is good at the back end, so they can develop the back end. These two can be linked with the intermediate code, right? So for implementation of that, there are different techniques are there. And some of the most important techniques are, one is the, so that is the postfix notation we can use intermediate form, and the second one is the syntax trees we can use, and third one is direct acyclic graphs can be used, and the fourth one is tree address code generations. But now in the high level languages we are using, that is another form of that one is, so that is the bytecode generation is also one type of code like this. So then, so that is how we are representing, these values are representing in the symbol table. So suppose when you are in the trees or graphs, it will be taking more time, more space. So that's why you can go for tree address code. In the tree address code, but when you are receiving the instruction from the high level languages, and how that will be converted into intermediate form. So then already I explained that. One is the short circuit, and how the variables are declared, and how the if statement will be working, how the statement. But most of the things are there. We don't want to go in depth about that. But so these are the some of the things in the intermediate code generation. So this is also a very important phase for gate, right? So here is suppose here is 14 questions are there. Suppose here is see that first one is see that gate questions. So first question you consider this. Consider the following C code segment L. Consider the following C code segmentation. For I is equal to 0, I is less than n, I plus plus. For j is equal to 0, j is less than n, j plus plus. If I mod 2 is equal to is 2, that is the true, then x is equal to x plus equal to 4 into j plus 5 into I. Y plus is equal to 7 plus 4. Which one of the following is false? According to this, which one is false? A. That is, here is they are given code. So that is the nested for loops, right? Two nested for loops and two expressions they are given. So which one is the false? The code contains loop invariant computation. The loop contains invariant loop computation. So that means invariant means that is whenever you are executing for the same values, it produces the same results. There is a scope of common sub-expression elimination in this code. So there is a scope of common sub-expression elimination in this code. So that means is there any sub-expressions? You see that there is a sub-expressions all there. So that means there is chances. You see that 4 into j, here is also we are using the 4 into j. So sub-expressions also there. So then it is there is a scope to reduce the program. Or here is when you are using this is the invariant means a block we can use, right? So here is when you are using that, we are using this is the block. And next there is a scope strength reduction in the code. Is there any scope reduction in the code? Like this, suppose if you want to multiply these two, we can use the shifting operators. Instead of using directly multiplication, we can use the left shift operator, right shift operator. So that definitely we can reduce the strength of the code. Fourth one is there any scope of dead code elimination in this code? Is there any dead code elimination? Dead code elimination means, so suppose in the entire program, so suppose throughout the program, if the code is not executing, that is called dead code. For example, after return statement, whatever you write, it will not execute. After return, so suppose in the C program we can write, so that is the print into main of this, the print, suppose if we are given that is the print hello and return. After return, if we are writing C is equal to A plus B or anything, it is a dead code. Dead code means the code will never execute. But when you see this code, every instruction is possible to execute. Every instruction is possible to execute. Here is every instruction is executing. So that's why, so then the D is answer. There is no dead code. So that's why you need not to eliminate any dead code. There is no possibility of eliminating dead code. So then answer is D is false. So in 2006, they asked this for 2 questions, 2 marks. I understood that. Just you see that answer. MR to inner loop invariant, it can be moved before inner loop. 4 into j is a common sub-expression appeared in the 2 statements. 4 into j can be reduced to j shift to by, so that is reduction of this. Suppose if the 4 is shifted to this, it will become to 4 to like this. Suppose there is a no dead code in the given code segment. So there is a no scope of dead code elimination in this code. So hence the only D is false. Understood that? So next second question. You see that a second question. Some code optimizations are carried out on the intermediate code. So code optimization, generally the code optimization can be taken at the time of generation of intermediate code. So then What are the things? That is, what is the cause? Some code optimizations are carried out on the intermediate code because. So in 2008, they are given for 1 mark question. First one is they enhance the portability of the compiler to other target processor. That means why they have to optimize, they enhance the portability of the compiler to other target processor. This is A. And the second one is B is the program analysis is more accurate on intermediate code than on machine code. Program analysis is more accurate on intermediate code than on machine code. C is the information from the data flow analysis cannot otherwise be used for optimization. The information from data flow analysis cannot otherwise be used for optimization. D. The information from the front end cannot otherwise be used for optimization. So that is when you have 4 options. Which one is the correct answer? So that is A. And then suppose if you want to increase the portability, so you need not to reduce the code. You need not to reduce the code size. Wherever you are doing the code, we can use like this, right? But here is the second one is that is program analysis is more accurate on intermediate code than on machine code, because we are not perfect on machine code, but suppose there is a chances of getting mistakes. So that's why. So if the program length is very large, program size is large, it is a very tiresome to write in the machine language. So that's why. So why code should be optimized means program analysis is more accurate on the intermediate code than on machine code. That's why. So mainly code optimization. In tomorrow's class I will explain the code optimization. So R symbol table. A code optimization can be done only on mainly on intermediate code generation means, because the program analysis is more accurate on intermediate code than on machine code. B is the correct answer. B is correct answer. So that is carried out. Next, third question. Which languages necessarily need heap allocation in the runtime environment? Which languages necessarily need heap allocation in the runtime environment? I think already we have studied the heap memory. Heap sorting. Heap means unused memory. Generally, heap is unused memory. For example, suppose when a program is executing, so for our students, most of the times I explain that. For example, while the program is executed, so that is divided into 4 parts. Memory is divided into 4 parts. Here is the heap memory, that is the empty memory. Here is the functions, it is a stack. It is a stack memory, and here is the global declaration, global variable declaration, and here is the program code. So that is depending upon the function size. If the function size is increased, by default it is a 64K. It is 64 KB. By default it is 64 KB in assembly language, right? But when you are taking that, if the program size is increasing more than 64, it takes the memory from the heap and it executes. Suppose if it takes the very less memory, then 32 bits memory and remaining 32 will be added to the heap. So this is the concept, heap memory, using of the heap memory in this case. So that is the thing we are using. But here you see that those that support recursion. Suppose when you have to use that, either suppose if that is when you are using the heap, it support the recursion, or those that use dynamic scoping, that is the dynamic scoping variables, or next those that allow dynamic data structure, those allow that their dynamic data structure. You can use dynamic data structure, or those that use global variables. So which one is the correct? A or B or C or D? So which one is the correct? Those that support the recursion, is it correct? No. Those that use the dynamic scoping? No. So that is here is, so but actually that heap is a data structure. That is those that allows dynamic data structure. That means already I explained that. Suppose if the function size is larger, automatically it allocates memory from the heap and automatically it is deallocated. So that means here is, so that's why we are taking that it is a heap memory. So it is the heap memory of this one. So that's why answer is C. For this one, those that allow dynamic data structures. Suppose if you want to allocate the dynamic data structures, we can use the heap memory. So for third question, answer is C. You see that a runtime environment means we deal with the dynamic memory allocation and heap is a dynamic data structure. So it is clear that those data that allows dynamic data structure necessary need heap allocation in the runtime environment. So heap is a dynamic data structure like this. You see that the common question is for two answers, 4.1 and 4.5. So two questions, this is the data, you clearly observe this data. The following code segment is executed on a processor which allows only register operands in its instruction. Each instruction can have almost two source operands and one distinct operand. Assume that all the variables are dead after this code a segment. So after that means these are the local variable. After execution, this will be a destroyed, right? You see that C is equal to A plus B, D is equal to C into A, E is equal to C plus A, X is equal to C into C. If X greater than A, Y is equal to A into A, else D is equal to D into D and E is equal to E into A. This is the code, right? But here is yellow, so that is only registers operands in this instruction. That means here is for processing they are using registers. One instruction, right? One instructions and two registers they are using. So first you understand the question based on this one. They are asking this. Suppose the instruction set architecture of the processor has only two registers. Suppose the processors are having two registers. That is 8 general purpose registers are there now. But if that uses only two registers, the only allowed compiler optimization is code motion. That is code will move, which move statement from one place to another place while preserving correctness. What is the minimum number of spills to memory in the compiled program? What are the minimum number of spills to memory in the compiler code? That means for execution of this code, how many minimum number of registers are required? How many minimum number of registers are required? So what is the answer for this? Either 0 register, either 1 register, 2 register or 3 registers, right? So suppose when you are taken the quadruple, 3 registers are required, 4 registers, but when you are using the triples, we can use the 2 registers or something like this is enough. For example, for this one you analyze the problem. B is the correct answer. So suppose here is to score. So C into C we are using. But in the first case you see that X is equal to C into C. Then here is, so to store C into C, it needs only memory spill. It is one memory spill. Because here is X is equal to, here is only one value is there, C into C. So C into C means only within the register the value will be incremented, double the value. So in the second case, you see that is uses previous same one memory spell to store C into A. For C into A means C is equal to C one register and A is another register. The number of memory spells are used in the above program is 1. So that is with the use of one memory cell and 2 registers, above optimization code will be executed. For this one, we require one memory cell and 2 registers. So this will be used in the registers. These are used in the register, and this can be used in the memory. That's why here is only one memory locations and 2 registers are sufficient for this, right? For this one, only one register is sufficient. One memory cell or one register is sufficient. C into C like this. But here is when you are using this operation, here is the two registers are required, and D, E, D also stored in the memory locations of this one. So that is the answer is what? That is the two. Answer is, so that is the two registers that will be required. I think you understood that, right? So generally we can use the minimum number of registers. So next question number 5. What is the minimum number of registers need in this instruction set architecture? So of the processor to compile this code. This code segmentation without any spill to memory. Do not apply any optimization other than optimization registers. So here is what is the minimum number of registers needed in the instruction set architecture of the processor to compile this code segment without any spill to memory. Do not apply any optimization other than optimization registers are allocated. So without, suppose there is, so but when you are optimizing this, you are getting two registers. But here is, suppose when you are not optimizing that, minimum how many number of registers are required. So that is the, so for the question, that is here is either 3 register, 4 or 5 or 6. So depending upon that, you see that the same in the intermediate form. So for everything, that is the no optimization, no code optimization means, so you have to use the, so that is the part report. That is the 4 operator, 4 values you have to take. Results R1 and R2. Then here is you can, for C is equal to A plus B, D is equal to T star B. For this one, we can use value. So that means 4 registers are required. Where is that we require? 4 registers. So then you see that A, B, C, D, E, F, G. So but when you are using that, E is equal to E. So here is only one register that is sufficient, and that is the, at least only one register is sufficient, and here is the 2 values are there, and these are memory location. That's why here is the 2 registers are sufficient to store the values, right? Here is the minimum number of this, that is the 4, 5 is, so that is the B, that is the 4 minimum registers that will be required. Which one of the following is false? Which one of the following is false? A basic block is a sequence of instructions where control enters the sequence at the beginning and exit at the end. That means a block of code. For example, in the if statement or otherwise the code which is written within the, so that is the open curly braces and closed curly braces, that is called the block. So in that block it will enter into the, at the beginning and exit at that. So that means it is a correct answer. And available expression analysis can be used for common sub-expression elimination. So that means here is, suppose when you are using available expression analysis can be used for common sub-expression elimination. And the third one is live variable analysis can be used for dead code elimination. And x is equal to x into y, that is x is an example of common sub-expression elimination. So which one is the correct? So first one is the block, that is the true. Why? Because, so that is within the block that will enter and that will exit. So second one is, so with available expressions we can analyze and we can find this some sub-expressions and we can eliminate them. So B is also correct. And C, live variable analysis can be used for dead code elimination. So that definitely while you are executing the program, the statements which are executing, those are called live, which are not executing, those are called dead code. So that's why C is also correct. But in the fourth one, x is equal to 4 into 5, that is equal to x, is an example of common sub-expression elimination. This is wrong. Why? Because so there is no common code is there. Suppose the common code means is the expression should contain the 2 or more same expressions. X is equal to 4 into 5. And here is we are taking, so that is x tends to this we are taking. So that's why here is, this is equal to, x is equal to, the output will be taken like this. That's why So, but here is when you are using, suppose x is equal to, suppose x plus 4 into 5, then there may be elimination. But here is D is the answer. In 2014, set 1, they are given for 1 marks. Then this sixth question is given for 1 marks, right? And you see that, so that is x1 is the value of consent folder not in. So which one of the following is not performed during the compilation? Which one is not performed? Which one of the following is not performed during the compilation? So while you are compiling the code, so which cannot be used? Either dynamic memory allocation, type checking, symbol table management, and inline expansion. So that is which one is not using? Either dynamic memory allocation or type checking, symbol table management, or inline functions. So that means here is you see that type checking we are using. So suppose when you are declaring the variables at the time of conversion, the compiler will identify either that is the type is mismatching, either variables are declared or not. So that's why type checking is done at the time of compilation. And symbol table management. That symbol table management, but whenever you find the first thing is the tokens or lexems, so automatically that will be stored in the symbol table. Tokens are stored in the symbol tables. That intermediate code is also done in symbol table. So that is the symbol tables also we are using. Inline expansion. Inline expansion means at the time of program, when you are using macros, whenever you are using macros or inline functions, we are also expanding. But we are not using dynamic memory location at the time of compilation. So that's why answer is A. When you can apply the dynamic memory allocation? At the time of execution, if the memory is allocated, that is called dynamic memory allocation. At the compile time, it will allocate. Suppose if you want to implement the dynamic memory allocation, we have to use the pointers, right? That's why for the seventh question, answer is A. For the seventh question, answer is A. So 10th question, you see that. So for a C program accessing x into x of I, comma j, comma k, that means the three-dimensional matrix. The following intermediate code is generated by a compiler. Assume that the size of an integer is 32 bits and the size of the character is 8 bits. So for the given code, which one of the following statement is correct about the source code of the program? Either suppose when you are using that, so which one is, suppose int x is 32, 32a is correct, or int x 4, 1024, 32 is correct, character, which one is the correct? X is declared as, either you have to declare like this, either you have to declare like this, either you have to declare, either you have to declare like this for execution of this code. But actually, either you have to declare. So that's why, so they are in 2014, they are going for 2 marks. But here is how much memory is required for this. You have to assume that, and based on that, we can calculate that. So that is the A is answer. X is 32, 32 into 8. So, but here is the same thing. For execution of that, we can use I into 30. This is the address for finding the two-dimensional or three-dimensional memory location. Integer size is 4 we are taken. Given integer intermediate code, we are taking this. So that's why here is the answer is A. So, but both are equivalent. That's why we can use either 32 into 32 into 32. Then by default also we can say that you did not to calculate entire thing. But here is 32, 32 and 8. So suppose here is you can declare the 32, 32, 8. But here is you are taking a 10, 24, right? But actually it will be taking the values of this. 9th question. So which one of the following statements are correct? Static allocation of all the data areas by compiler makes it impossible to implement recursion. Automatic garbage collection is essential to implement the recursion. Dynamic allocation of activation recursion records is essential to implement the recursion. Both heap and stacks are essential to implement the recursions. So either 1 and 2 are correct, or 2 or 3 are correct, 3 or 4 are correct, or 1 are. So that is you find the ABC. That is the ninth question of that. So here is the first is a static allocation of all the data areas by compiler makes it impossible to implement the recursion. But when you are using the static memory allocation, so then it is impossible to use the recursion because the recursion is depending upon the input value. Suppose memory usage. Suppose, for example, factorial of 2 when you are given 2 times it repeats, factorial of 10, 10 times it will be repeat and store, factorial of, so that is dynamic. So that is the A is, so that is A is the correct. And the next one is 3 is a dynamic allocation of activation records is essential to implement the recursion. That is the dynamic allocation. Activation records are implemented. That is the pointer shared. So that means answer is D. So now you see that consider the basic block given below. A is equal to B plus C, C is equal to A plus D, D is equal to B plus C, E is equal to D minus C, and the minimum number of nodes and edges present in the DAG representation of the above basic block represents what? So that is the minimum number of nodes and minimum number of edges for representing this graph, right? So here is sometimes you have to see that. So that is the date code elimination. So suppose you calculate the values. So minimum there when you are asking the minimum, you see that 2014 and for 2 marks they ask, right? You see that calculation. So you see that A, so that is you are using A is equal to first to last one you are taking A is equal to A plus B. So that is the code where A is equal to A plus D we are using. That means here is interchanging. A is equal to E plus B and here is A. So that is the A is there. So then A D minus B. So then because here is A is equal to E plus B we are writing. So then in interchanging. So D, so that is the D minus B. We can use like this. So next A is equal to B plus C. Suppose here is you see that B plus C. A is equal to B plus C. C is equal to this one. You see that A is equal to E plus B. A is equal to E plus B. First we are writing here. So suppose A is equal to E plus B. We are writing. So after that A. So in this case, suppose here is the D where we are replacing that D. So that is the C can be having like this. So suppose here is the E and the C. C is equal to A plus D. And here is A is equal to this one. Here is the C is replacing B minus B plus D. B plus D is equal to where? B plus C is equal to D. You see that B plus C is equal to D. So then here is A is equal to D minus B. Why you got D? So that is the B plus C. D is also B plus C. So then B plus C is replaced with D. So then D minus B, D are like this. But when you are using that B plus C is expression. So here is a, so how many nodes? 1, 2, 3, 4, 5, 6 nodes or 7 edges. So this is the 2 times that we will suppose B plus B we are writing. So that expression like this. We are substituting the values. A is equal to E plus B we are taking, and the next that is here is for this A, for this D we can write B plus C. So that is the B plus C is replaced with the values of this one. Code 11. The least number of temporary variables required to create 3 address code in static single assignment form for the expression Q plus R by 3 plus S into 5 T into 5 plus U V by W. So that is also 2015 set 2 marks. So that is the minimum number of temporary variables in the we have to use like this. So you see that answer. So first we can take that is the R by 3 and R by 3 T1. So Q plus T1 expressions we can solve like this. T3, T4, T5, T6, T7. Just we are using that. So for each and every expression we are using temporary variables without using that. So the 8 temporary variables are required for this. R plus 3. This one is next. So T1 plus Q. You have to add. Next. So that is T2 plus. So that is the S you have to add. Next. So T into 5. That is our star will be executing. E3 minus like this 8. So that is the minimum is 8 registers are required for this. And in the so the 12th question in the context of abstract syntax tree and control flow graph, which one of the following is true? So that is the answer is both S and G. Level node 1 be successor of the node 1. In the input program, the code corresponding to T2 N2 is represented after the code corresponding to N1. So that means in the 12th one, so suppose C is the correct answer. The maximum number of successors of the node in a ST, AST and CFS depends on the input program. So that is C is the answer. So here you see that consider the intermediate code given below. So you see that code, the number of nodes and edges in the control flow graph constructed for the above code. Suppose you have to construct the graph. For example, you see that, these are the expressions, the two statements, looping statements are there. If j is less than equal to 5, g is. So then you divide this code into number of blocks. For example, you see that the declaration will be done outside, right? I is equal to 0, j is equal to 0. The block of code is written like this. And if j is less than 5, then go to the state. So if j is greater than 1, then I is incremented and j. So suppose this is just like two-dimensional in a state for loop, two for loops. So for this one you see that. But we can write the code, same code in the graphical representation. When we are writing that, so suppose I, j are the 1, 2, 3, 4, 5, 6. So 6 are the nodes and so edges are 7. That is the 1, 2, 3, 4, 5, 6 and 7 are the edges. 14th question, you see that one of the purpose of using intermediate code in compiler is, directly I took this from this. So that is the make parsing and semantic analysis simpler, improve the error recovery and error report, increase the chances of reusing the mission independent code optimization and the compiler, improve the register allocation. So that is what is the answer for this 14th question. So that is the making parsing or semantic analysis simpler? No. These are performing before the intermediate code. Improve error recovery and error reporting. So this is also not correct. Increase the chances of reusing the mission independent code optimization in the compiler. So C is the answer. Improve the register allocation. This will be done at the code generation process. So that's why here is C is the correct answer for this. Right, C is correct. Fourth one is consider the grammar rule. E can have the form of E1 minus E2 for arithmetic expression. The code generated is target to the CPU having the single user register. The subtractive operations require the first operand to be in the register if E1 and E2 do not have any common sub-expression in order to get the shortest possible code. So suppose here is when you are using the statement E is equal to E plus E1 minus E2. So either in this case, suppose only one register is there. Only one register means, so that is another one will be stored in the memory location. So that's why here is, so first one is we can take that is the E2 should be evaluated first. Suppose E2, because why E2? E2 is second time we are reading second carrier. E means we are reading second. So first that will be that value will be stored in the memory. That's why in the register. So first we can use it. And E1 is in the memory. Suppose if it is E1 is in the memory, so again you have to load it into the register and you have to perform. That's why always that is the E2 will be the available first case. So the last 16th question, some code optimization are carried out on the intermediate code because, so already I explained that, the chances portability of the compiler to other target processor, program analysis more accurate on intermediate code than on mission code. The information from data flow analysis cannot otherwise be useful for optimization. The information from the front end cannot approach the values of that. C is the same answer. Already previously I put that question. They enhance the portability of the compiler for other target missions. So this is the thing. Thank you. So that is today I am closing this class. So I think you understood this. Thanks for your patience and listening my lecture. Right? So I can give your opinion on this lecture also. So thank you. Thank you.